All right, suppose I have a container filled with some liquid and the density of the liquid is rho. And so how does pressure change within the liquid? So let's draw something. So here's my container, all right? And it's filled with some fluid here. And the density of the fluid is rho, that's the density. At the surface of the fluid, there is only air on top of it, so so the container here is at the surface of the earth. So here it's just atmospheric pressure, just outside. And the question is, somewhere deeper here, at depth h, what would the pressure be? What would the pressure be here? The way we're going to do this is, imagine you're there, and you ask, what's on top of you? How much pressure is on top? What would be on top of you? Well, let's see. You will have, let's take let's say the pressure here is P1, pressure P1. The pressure here will be some pressure, it's P2. And we're going to draw a virtual cylinder, so, right? The fluid is made of many, many parts, and I'm going to choose one part and focus on it. And it will be a vertical cylinder that looks like this, right? And it's length h. Length h, all right? This is my cylinder. And the cylinder will have cross-sectional area A and height h. So the volume will be the cross-sectional, the area of the cylinder is A, the depth is h, so the area will be, the volume will be the area times the depth. The area is pi r squared, but I will just write it as A. That's the volume of the cylinder. So how much mass is in this cylinder? Well, remember, density is mass over volume, so the mass will be the density times the volume. So the mass of the liquid contained in this cylinder, how much mass is it? It's the mass will be the density times the volume, and that is the density times A times H. Okay? Now, the liquid is not moving. It's in hydrostatic equilibrium. So it's in equilibrium. It's not moving. So if it's not moving, we're going to apply Newton's laws to it. In particular, we're going to say the net force on it has to be zero. If the net force is not zero, then it will move. Right? Newton's laws still apply. So what are the forces on this cylinder if I isolate it? So let me take my cylinder by itself. Here it is. What are the forces on it? Well, there is pressure here. Remember, pressure always acts perpendicular, so there is the force due to the pressure here, F1. And then there is the force due to the pressure here, F2. And then there is gravity pulling it down, the weight, and that's mg. And that's it. Those are the forces, right? There is force from the fluid above it, and there is force from the fluid below it. And then, oh, by the way, there are forces to the left, but we're just concerned about the motion in the vertical direction. It's not moving vertically, and it's not moving horizontally. We'll talk about horizontal in a moment. So the net force has to be zero. So let's say here is the positive y direction. Then what are the forces? You got F2 going up, and then F1 going down, and then mg also going down, and they have to add up to zero. Right? That's the net force, and it has to add up to zero. Now, what is F2? Well, it's the pressure 2 times the area. Force is pressure times area. That's why we go to pressure. You will see things will cancel, and you get nice things. Because you see the force here will depend on how wide the cylinder, but the pressure doesn't. It's just one value. So it's the pressure at point 2 times the area at point 2, but it's a cylinder, and the cross-sectional area is constant. And the force at point 1 will be the pressure at point 1 times the area. And then minus mg, but the mass is the density times the area times the depth, density times volume. Rho A H, that's the mass, and then times gravity equals to 0. And notice the area simply goes away and only the pressure remains. And so we have the pressure at point 2 will equal to the pressure at point 1, move it to the other side, plus rho GH, rho GH. So as you go deeper, pressure will increase and it gets larger. The deeper you go, the larger the pressure. So let's take an example of a submarine 300 meters deep into the water. What's the pressure there? So here is the water, and the submarine, let's say, is here. And the question is, what is the pressure here? P2 equals to what? Equals to what? The depth is 300 meters. And you will see it will be incredibly large, huge. So what's the pressure? Well, let's see. We'll take the pressure here, P1. That's just, it's at the surface of the water, so it's just atmospheric pressure, PA, P atmospheric pressure. I think the book calls it PAT or PATM. Let me just, I would just call it PAT, at, for atmospheric pressure. So P2, just apply this. P2 will equal to P1 plus rho GH, rho GH. And P1 is atmospheric pressure, so it's 1.01 times 10 to the 5th plus. I would just say it's fresh water. I mean, we could use ocean water or sea water, which is about 1,050, 1,030 kilograms per cubic meter, but let's just say it's fresh water. So the density is 10 to the 3. Gravity is 9.8. And then the depth is 300. So that's 3 times 10 to the 2. So we get 1.01 times 10 to the 5th plus 10 to the 3 times 10 to the 2 is 10 to the 5th. And 3 times 9.8, I believe, is 29.4. 29.4. And so you can see this. This is about 29 atmospheres because it's 29.4 times 10 to the 5th. And this is 1 atmosphere. So it's approximately, let me write it this way. So it's approximately 30 atmospheres. Let me add that first. So we get 1.01 plus 29.4 gives me about 30.41 times 10 to the 5th pascals, newtons per square meter, and that's approximately 30 atmospheres, 30 times the atmospheric pressure. Okay, about 30 times the atmospheric pressure. I approximated. I mean, obviously, if you use seawater, it would be maybe 31 or so. So that was the variation of pressure with depth. Now, if you're at the same depth, do you have the same pressure? And the answer is yes, but let's argue. So we said, if you're here and you go right below it, if the pressure here is P1, the pressure here is P2. But what if I go across? If the pressure here is P2, is the pressure here also P2 at the same level? The answer is yes. Let's see why. Newton's laws again. Let's see. Here's the argument. It's always cylinders of water or something virtual. So here is the argument. Here is the fluid. Let's take our virtual cylinder. But I'm going to orient it horizontally, like really thin horizontal cylinder. And let's say the pressure here, let's say I know the pressure here is P2, and here it's, I don't know, maybe it's P2 prime, maybe it's different, And we will see that they are the same. And the area here is A. The area here is A. So, we talked about the net force earlier in the vertical direction. Here, this horizontal cylinder is not moving up and down. It's also not moving left and right. Let's see what the net force in the x direction is, in the horizontal direction. What is the net force in the x direction? Well, for this cylinder, you got P2 prime times the area this way. So let's call it F2 prime to the right minus F2 prime. Remember, pressure always applies, the force is always perpendicular to the surface. So minus F2. I always keep in mind that after all, what's causing the pressure? It's collisions of molecules hitting you from either side in contact with you. And so they can only hit you this way, perpendicular to you, not this way. They don't, I mean, there are attractive forces, but here we're talking about the ones that push you. And so the net force has to equal to 0. So F2 prime has to equal to F2. But F2 prime is P2 prime times the area, and F2 is P2 times the area. The area cancels, and therefore P2 prime will equal to P2, as long as you're at the same height, at the same depth. Okay? If the height changes, then the pressure here, the pressure at the bottom will be larger than the top. But we're talking about horizontally. Okay? So let me do an example here. Here's an example. Why, for example, if you have a liquid, why it has to have the same level. So let me just show you here. For example, let's say I have a container here, like a U-tube shaped, like a tube that's U-shaped. And the liquid, if I fill it with water, it has to have the same level. They have to have the same level here. And why? Why doesn't, maybe this side is narrower, you might think the water should be a little higher. Why? The answer is, it's exactly the Newton's laws that led us there, so we will come to this conclusion. We'll say, let's say the depth here is h on the right-hand side, h right, and the depth here is h left. Let's say they are not the same, okay? So, I don't know, maybe they are not. First, let's start here. The pressure here is P1, the pressure here is P atmospheric, P1, and it is equal to the atmospheric pressure. P atmospheric, that's P, the pressure on the right, the pressure on the left. And let's get to the bottom of the container. At the bottom of the container, we're at the same level, right? We're at the bottom of the container. So this is P left, this is P right. Since they are at the same level, then they are equal. So now, how do I get P left here? Well, it's P1. Remember, you got P2 equals to P1 plus rho GH. So the pressure on the left will equal to, the pressure on the left is equal to P1 and plus rho GH on the left. Rho GH on the left. This is rho GH. And then the pressure on the right here will also be P1 plus rho GH on the right. But the pressure on the left has to equal to the pressure on the right. Again, for the argument with that long cylinder, if this pressure were larger than this, then the cylinder will either move this way or move this way. The water has to move, but it's in static equilibrium. It does not move. We will talk about water in motion in a moment. I use water as just a typical fluid, but I really mean any fluid. So we got this. These two are equal, so these two are equal. So we get P1 plus rho GH on the left equals to P1 plus rho GH on the right. And P1 cancels with P1, subtract them, and then divide by these, and you get H on the left, the depth on the left has to equal to the depth on the right. So that's one way to figure it. Okay? All right, so that's good. Now, let me show you another example. Let's say I have this container is open on both ends. What if of a container that looks like this. You have a container long this way. Now, if you just fill out with liquid, it will overflow. It has to be at the same level, and so anything extra will flow from here. You cannot have this one here. However, if you block, let's say this container, I'm going to seal it here, right? You put a lid and you weld it or glue it. Now you can fill, if you fill the water up to here, the water will get to here. I'm sorry, let me do it this way. If you fill the water up to here, the water will get up to here. If you fill it to here, then it will get to here. It will get to here. But if you fill more, well, it can't overflow, so it can get here. It wants to overflow, but it can't, because the wall here will push it down, so it applies the pressure to it. Earlier it was atmospheric pressure, because it was open to the air. Only the air is pushing it down. But now, you have this container pushing it up from the top, applying a normal force to it. So now, suppose the fluid we're considering is up to here, right? And let's say this is H on the right, and this one here is H on the left. And the question is, what's the pressure here? How much is it? How much is it compared to the pressure compared to here? What would the pressure on the right given HL and HR? And HL is larger than HR. Well, let's see. We will start here at the bottom. The pressure has to be the same, right? The pressure here has to be the same here as here. Pressure at the bottom, let me call this one here P2, and this is P2 for the same argument. If it weren't, then the fluid will start to accelerate and move. So P2 has to equal to P2. And this one here, I'm going to call it P on the right, the pressure on the right there. So the pressure on the right, whatever it is here, plus rho GH will equal to P2. So we get this P2 will equal to the pressure on the right at the top here, plus the additional pressure due to all this fluid, rho GH on the right. How about here? Well, that's the pressure here, that's P atmospheric. That's P atmospheric. Plus rho GH on the left. Okay? But P2 has to equal to P2. I drew P2 here, so that's P2. So these have to be equal to each other. Okay? They have to be equal to each other. And so, let's see. So we get the pressure on the right, the pressure here, will equal to P atmospheric. Move this to the other side, plus rho GHL minus HR. I factored that. So I moved this to the right and factored rho GH. But what is this? This is the pressure here. So the pressure on the right is P atmospheric plus rho GHL minus HR. This is HL minus HR. And so the pressure here plus rho GHL minus HR is this pressure. So we conclude that the pressure here is the same as going here at this depth. That would be the additional pressure. Now, if you keep making this column really long, at some point the lid cannot handle the pressure and it just pops, and then it just opens if it's not strong enough. Okay. The next question is, it's all good, but how do we measure pressure in the first place? How do we measure it? How do we come up with a measurement for it? An apparatus that tells me what the pressure is right now. I mean, I could use that spring, that vacuum spring cylinder, stick it inside a fluid, then it will give me the pressure. The problem is it can't give me atmospheric pressure because, well, maybe I have to take it to outer space and then bring it back to inside the Earth, and then it will compress. The spring will compress due to atmospheric pressure, and then I can measure the pressure that way. Well, you don't have to go to outer space. In fact, people didn't go to outer space until what, the 1960s. So imagine you're in the 1800s or 1700s. How would you measure pressure? Well, here's one way measuring pressure. It takes advantage of the concepts we just mentioned, right? You see, all of it is following from Newton's laws. So measuring pressure, here is one way. Pressure. So here's one way. Take a liquid, and preferably a dense liquid so that the apparatus will be plausible. You will see in a moment why. And the densest liquid that we can have, and it's relatively cheap, is mercury. So take a container here of mercury, and it has lots of mercury here. All right. Then take a container. It looks like this, right? Suck all the air from it. So it's completely empty vacuum. So just suck all the air. It will never be empty vacuum, but imagine for a moment as close to vacuum as you can. So it has nothing. So I'm going to just like put my finger here or put a lid. I sucked all the air, so this is completely empty. Empty. So what's the pressure inside? The pressure from the inside is zero, because there is nothing. If you put any object here, it's not going to experience a force because there is nothing to hit it, to collide with it. So the pressure inside will be zero. In other words, the walls of the container from the inside are nothing is pushing on the walls because there is nothing to push on. Now you take this container, you put it here, you flip it, right? So you put it here, so what you get is this. Take the container, flip it upside down. When you flip it upside down, take the lid off. So you take the lid off. So when you take the lid off, here's what happens. The liquid will go up to fill the container up to a certain level. Assuming, let's say the container is long enough that it will fill it to a certain level. It will not flow all the way in, all the way to the top. If it flows all the way to the top, repeat the experiment, get a longer tube, do it again. Try it. If it flows all the way to the top, you have the wrong, it's not long enough. Redo it until you get a container that's long enough that the fluid does not sneak in all the way to the top. Why? I want this to be zero, so that's my reference point. It will still be vacuum. You see, it was vacuum until the fluid got here, and now it's still empty here. So the pressure here, this is empty also. So the pressure here at this point, the pressure at this point inside is zero, because there is nothing. Okay. Now, what's the pressure here, just outside? Well, that's open to the air, so it's atmospheric pressure, P. Atmospheric pressure. Okay. Now, we argued that if this is the fluid, this is fluid, it's all connected with each other. So the pressure here, and the pressure here, they're all equal to each other. And let's say this height here is h, the depth here is h. So here it's atmospheric. How about here? For the container, it's zero here, but it's atmospheric there. But let me call this P1, and the pressure here is P2 here. So I know that P2 will equal to P1 plus rho GH, rho GH. P2 will be the atmospheric pressure, is the atmospheric pressure, P atmospheric pressure. P1, here it's zero, You see, that's why we wanted it to be vacuum, so that we know for sure. That would be our reference point. That would be 0 plus rho GH. And that corresponds to the atmospheric pressure. Now, people did experiments, and when they used mercury, using mercury as the symbol Hg, the density of mercury is 13,600 kilograms per cubic meter. When they did the experiment, they found that H, near the surface of the Earth, rises to about 0.76 meters, which is 76 centimeters, which is 760 millimeters. You probably have seen 660 millimeters of Hg, of mercury. That's the atmospheric pressure. So the atmospheric pressure then would be P atmospheric. Let's see how much it is. It will be rho, the density, that's 13,600. See, we can measure the density. Just give me the mass and the volume, I can measure the density. Gravity has been measured, and it's 9.8. And H, we just measured it, it's 0.76. And we get 13,600 times 9.8 times 0.76. And let me get my calculator. So I hope you can predict what the answer should be. It should be 1.01 times 10 to the 5th, right? About 1,000 times 10 to the 5th, about 10 to the 5th. So 13,600 times 9.8 times 0.76, and that gives 101,000. I'm sorry, 101,000. 1.01 times 10 to the 5th. So that gives 1.01 times 10 to the 5th. Newtons per square meter. So now you have an apparatus that can measure the atmospheric pressure, and you have an apparatus that you can reliably measure pressure. There are better ways to do it, but that's what it is. Now, if you were using water instead, so now we know what the atmospheric pressure is. We know how to measure it. It's 1.01 times 10 to the 5th. If you were using water, a column of water, you see, instead of, let's say I know the left side, this is 1,000 for water, this is 9.8, and I want to know what H is. You will find that H will be about, I think 13 meters or something like that. Or, I'm sorry, about 10 meters or so. It would be larger, much larger than this. And nobody wants to work, 76 centimeters is about this much, or maybe this much. Anyways, it's less than a meter, about 2 feet. If you have water, on the other hand, that's 10 meters, it's an apparatus nobody wants to have. You cannot have it inside this classroom. It's about, 30 feet tall. That's pretty high, about 3 stories. So you don't want such an apparatus. This is more convenient. That's why people use mercury. All right, in the next video, I'm going to talk about hydraulic lift, and I will talk about Archimedes' principle and its applications. And then we will get to Bernoulli's principle. The fluid will start moving then. And then we'll talk about Young's modulus and the elasticity, which is the part of the top of this chapter. So far the fluid is at rest, and it will remain at rest for the next video also or two, and then it will start moving when we do Bernoulli's principle.